Let's begin by exploring the fascinating process of phase transitions, particularly from gas to liquid. In a closed container, as temperature drops, the system undergoes a discontinuous change at the gas-liquid boundary. Initially, the gas phase is uniform, but as cooling continues, droplets of the denser liquid phase start to form and grow. These droplets persist longer and eventually absorb surrounding gas molecules, becoming large enough to scatter visible light. This is why clouds appear milky white. This process is distinct from critical opalescence and highlights the unique behavior of matter near phase boundaries. The transition is marked by rapid droplet growth, especially at the critical point, where liquid and gas phases coexist in equilibrium. Pressure can shift volumes of gas into the liquid phase without energy cost, emphasizing the compressibility differences between the two states. Moving deeper, let's examine the spatial correlations that distinguish liquids from gases. While both share certain symmetries, liquids are much denser and less compressible. The arrangement of particles in a liquid is governed by a balance between repulsive and attractive interatomic forces. When a particle occupies a position, no other particle can be found within a certain exclusion zone, thanks to repulsive interaction. Attractive forces are largely satisfied due to high density, resulting in strong local packing. This structure is visualized using the radial distribution function, which shows how probability varies with distance from a central molecule. The first peak represents close neighbors, and further out, oscillations indicate layered molecular arrangements that eventually stabilize. These correlations are key to understanding liquid behavior and are mathematically described by functions like G, R, and S, Q, linking spatial structure to scattering patterns. Finally, let's discuss the profound relationship between symmetry and rigidity in condensed matter. Liquids and gases possess the highest symmetry, being invariant under translations, rotations, and reflections. This is described by the Euclidean group. Their environments look the same everywhere and in every direction, simplifying mathematical descriptions. However, when water transitions to ice, continuous symmetry is broken. This is only invariant under specific operations that preserve its periodic lattice, resulting in lower symmetry but greater rigidity. This rigidity is essential for the existence of periodicity in solids and is characterized by elastic constants that resist thermal fluctuations. The water-to-ice transition is a classic example. At high temperatures, water is isotropic and homogeneous, but as it cools, potential energy dominates and a rigid crystalline state emerges. This broken symmetry phase is what gives solids their unique mechanical properties.